equals 0. Let's see, partition equals 0. This equation tells us if that equals 0, this is either equal 0 or equal pi, right? Or equal 1. So this actually t equal, this will be exactly this part. This actually, this is a line way bar equal minus down, right? So we bar because here, this is a line, for example, if I have a way bar here, this actually, this guy has become negative, this is positive. So exactly, straight lines. So this actually t equals 0 case, then you want to say what's happening when I say t equal T1 greater than 0. Can you imagine where is this line? T is finite. Let's see here, the finite, right? What about this point? This is a point where way prime equal half a pi, w prime equal minus half a pi, right? This minus this one equal pi, 0. This equals 0, right? So this is always a point. This is always a point. So you will say this is always a point. What? 0, 0, 0, 0. 0 equals 0. Okay. So we'll go like this. Negative case will go like this. Okay. This is a t equal constant heavy surface. This is actually t greater than 0. This is t less than 0. This is t less than 0. T greater than 0. Remember, yesterday we found this actually in this region the time actually gives negative arcs. Okay? Now I'm going to ask some questions. This is the two regions, right? 1 prime. Can we send a particle from 1 to 1 prime? Can we construct some time-like trajectories from 1 to 1 prime? This is 45 degrees, right? This is 45. We narrow, right? Because that means this is two regions cosella not connected. So that's why normally we think our universe maybe does not exist. You see, you cannot send a particle. Because if you send a particle, this is a line to come 45 degrees, right? This actually is a line to come 45 degrees. You send a particle here, your particle always go like this. There's no way for a particle to come here. Coming here, you get actually this space-like trajectory. So 1 prime and 1 is causally disconnected, right? Yeah. What about this region? 2 prime and 1 prime? I can always send the particles to this region, right? I can, what about this 1 prime and this one? I can send a particle line, right? So that's some people think, okay, we have wide hole emitting particles, then the particles interact with each other, talk to each other, finally form a black hole. There is possibility from here to this one. The same thing from here. Of course, you can also start from here, collapse inside black hole. This is what we normally understand, right? So we just, you really want collapse black hole or 1 prime to black hole. But there's also here possibility. The 1 hole emits some particles, and the particles, because they have attractive force to each other, then finally they form, they actually focus into a single arc. Right? So there are some models, like physical, mathematical models to describe this. Especially in the early of the 90s, several people from the US reconstruct this one. And that was actually become a world famous model. And now people actually still think that this actually exists in our world. We do not know. Okay? So this actually, the current status, this panel diagram, very easy actually if you sit under to know how to draw this one. Okay? So this, any question about this part? So this actually is for the Schwarzschild case. This all those standard now. The question is, what's happening, for example, when we consider more general case, more complex case? More complex case, what we do actually, you just start it one by one. This actually our next lecture, because we have 10 minutes. Follows the next lecture, we have a lot of material to cover. I would like to use this 10 minutes to see something, then later we continue. So this actually, this is my notes. Actually, while teaching general relativity, I summarize. Unless I didn't find any place you can find, you can find from someplace. Okay. So this part, something you can say, I summarize the idea. You can use this one to deal with any kind of space-time. This note actually I consider ds squared equal FRD t squared minus HRD r squared minus r squared d squared. But with a particular case, H equal 1 F. Right? Remember, Professor Sushant said this is a static most general case. What's happening if I have some singularity here? So this is a question I would like you to think about this with this lecture. Just to give you a hint, the extent for this is the same. The only thing you need to assume F will go like R minus, let's say I have 1 and R equal N equal as G R. Now your H needed to have R minus R and H hat R. If you have this kind of behavior, then you can use exactly what I did here for the more general case. What's happening if not hit this one? If not on this one, nobody knows how to do this. Not only me. If you know, let me know. Okay? Very complex.
Is R and over here?
This just has to be Y or R because this becomes single. Like a F case, right? Yeah. So the single R only, you see here, F actually 1 is this is H actually broad. S like is exact case. So in the general case, you will see most cases are like this. Okay? Like China solution, Kerr solution. But there are some cases maybe it's not. If it's not, we don't know how to deal with this here. Okay? So I'm going to actually consider in my notes, I'm going to consider this case 1 over FR. After this lecture, you can do this, no problem. The same thing, you can figure out the only definition is define the G different. Later you will say what's the G. Okay? Yeah. So this actually, let's consider quickly lecture. This actually, I use different patterns, but let's say Paris diagram too. Okay. This is for the general case. For the general case, we consider space-time ds squared equal f r dt squared minus dr squared f r minus r squared. Okay. For the slight shadow case, we all know this is 1 minus 2m or r. But if you have a charge, then we have this one, right? This is actually called, this is a charge case. If the charge equals 0, we have a charge. Well, you can have a multi-zero. This is actually one example, but here actually we will assume my f equals 0 is actually our kind of n rows. So I equal I equal 1, 2, 3. But all the actual roots are real are different. If we have two of them equal, we know how to do this. If three of them equal, nobody knows how to do it. Okay? So if you have something like this, r minus rn, 1/2 the extension is not analytic, it's not unique. So physically, it's difficult to define that level. Because you can make an extension, it's not unique. But you can have something like this, not unique, right? So that's actually complicated, so that's why we just consider different rules and all of them are real. Okay. Then,
Sir,
yeah.
when we have different horizons,
Yeah.
horizon 1, 2, 3, 4,
Yeah.
which one, what is the criteria for which we will be taking it as an event horizon? Which one is to be the event horizon?
Okay, good. Yeah, the event horizon normally we consider the large star, with the large star, most of all seven. Then the inner horizon actually we have, you can have many, multiple horizons. But like the charge case, we have two. We have this, if you get this r, this equals 0, you have r plus minus equal m plus minus m squared minus e squared. You can use it fine.
But if you have digital, then this is not correct.
Yeah, if it's different, no, I'm talking about,
Yeah,
this is charge, right?
flat.
Yeah.
Flat.
Yeah, this is actually charge case.
Yeah.
So this is actually for E less than M.
Yeah.
You have two. But the E equal M, you can see these two guys like degenerate, then you get R squared. R squared, we know how to do this, I will talk. But if I have, let's see, if I have something F equal R minus R less than 0, sure, we don't know how to do this. If 3/2, we don't know how. R minus R0, 1/2, we don't know how. Why? Because this actually, the extent is not unique, it's not analytical, right? So you can use this if you take it directly, we're not. Okay, so,
Yeah.
yeah, any questions? So we will actually, once we get this case, what do we do actually? You just, let's say here, I'm in here, this is my F, R, and you have something like many rules, right? And we consider all of them a single. There's a possibility I have something like the two of them, let's see, there's a possibility, this is the two rules we set. We can deal with this one. But if you have something like R minus R0 cubed with the number, we will actually consider, first consider there's a difference, then we come back to consider the pattern. So we have like 1 minute, maybe I stop
Yeah,
here.
yeah, yeah.
Then next we'll continue.
Yeah, okay. Thank you.
So let's start our lecture 8. So this actually is the most general metric. Professor Sushant just told us this actually with the Fourier symmetry. This you can also deduce from the most general one I just derived with TR independent. Right? There are two functions. So here actually we consider this case. Like what I said, you can actually consider the same even for any edge, as long as f equal 0. Let's say here's r equal Rn. Now h should also have something like edge head. Here you have 0, let's say R1. R minus R2, R minus R. As long as they have the same rules, this measure will apply. So this is only one we done. R1, R2 is F equals 0. Sorry, let me see. Where F equal, let's see, R minus R1, R minus R2, R minus Rn, F, R height. Okay? So,
R1, R2, R3 are the position of the horizon.
this is actually called the horizon. The largest one is called the Yuan horizon. But each of them is called horizon. So the most, this one, okay, good. This is actually R. So we have, let's see, R1, R2, Rn. This one is called Yuan horizon. All the rest is called Yin horizon. Okay, this is the Yuan horizon. So there are possibility, different theory you will say, even in Einstein, if we have a matter, this could be possible. Okay, so we consider all in the case H point called simple singular point. Okay, so then you can see even for the general case, this also you can apply, but this we need to have H at R minus R1, R minus R, which means the singular property should be the same in this one. As long as even H is different from 1 or F, if they have this structure, you can use to the measure to generate this case. Okay? The only difference you will see, this is a function I'm going to introduce a G function. Okay? So if you really understand the part after this class, you should be able to do this. Yeah. What we do actually is the following. The strategy is the following. Now, you see, if we have some singularities, we are either here or either here, right? You cannot have really in between. So, critical extension, the main idea is I just try to put these two regions together. Then, like papers, I glue them together, this part, then glue another part. So, the idea is very simple. If you, then let's say I first glue this part together, after that I glue this part together, then finally I get a copy. So we just do one by one, then you just put them together. So if it's one by one, then you will know, okay, we already did a Schwarzschild case, then something will be similar. So exactly. So I'm going to first give the general ideas, then we can apply, come back to Einstein, Schwarzschild case, you say, oh, that's simple. But later you can consider it as a charter case. Charter case, like what I said, we have two horizons. Even for example, if I have a cosmology constant, I can have also two horizons, right? So that's in principle, you can work out all the details. Any question about this? Okay. So, now the first thing we want to like to see, okay, we have actually this is my TR is not F anymore. This is R. I want to see one observer start with, let's say, R equal 0. This is actually the trajectory of this observer, right? So, you know, this velocity of this observer will be U mu equal F minus 1/2 delta mu t. This is a timeline. This is not necessary. This is actually listener observes. This actually observes just sit on R equal constant, then moving with the time, structure of time. Okay? So then we actually introduce a quantity called acceleration, mu. And mu, u, mu, nu. The second color always actually is a current word. Right? So this is actually u, nu. So you will see this will equal, I call kappa alpha delta mu r. There's only the acceleration, there's only one component. Okay, easy purpose. This is the current word. U, mu, nu, similarly equal. Similar. So where kappa equal r equal 1/2 f r prime. So this actually, this is the full velocity. This is the acceleration of this person. So this actually observes sit down with r equal constant there. Then we have r. This is called surface gravity. So surface gravity here is very important. Surface gravity means actually if you can say r equal constant surface, right? So what's the surface gravity? Exact corresponding to the acceleration. The acceleration. So this guy is phenomenal. If you have a black hole here, of course this will feel some forces. This is actually fixed r. This is exactly the surface gravity. Like what we are sitting here. Our Earth actually is like a ball. We are on the surface. So our weight you can consider surface gravity, right? This is the same thing. So we're here. So this actually equal. This part. This actually derivative. I have this one. Now, of course, if I consider this actually under the horizon r equal r. So this actually the surface gravity of the horizon r equal r. So this actually we have this. So now, once I have this, I come back here. I will still use this actual relations. This will equal f r dt squared minus h r f r dr squared minus r. So I define my dr star or r star equal h r f r dr. This is, let's say, this equation 1, this is 2, this is my preparation. I call this equation 8. So later I will erase here, that you can find from my lecture notes. So what I'm going to actually assume the following. I will focus only on one of the horizon. Let's see RF. Now I assume my R equal R minus I over GR. So where GRI different from 0, right? If it equals 0, then you have some. So you see here, then I can do the following. Once I do this, actually, I'm going to expand GR equal sigma I equal 0. Let's say I equals 0 to infinity. A and R minus R I. Well, A0 is different from 0. Why? Because of this one, right? R equal Ri, so A0 term is different from A0. This is the assumption. And this actually I equal di dri dr, right? So this actually I equal R. So I want to see you can plot here. Now again, for general case, you just simply need to simply put H R equal R minus R A H right? H R I different from 0. Then redefine something like G. So the same thing, so I just want to let you know, this actually can be generalized to the most general case. So once I have this one, you can see what's happening. I'm going to actually put it here. Now I will use something here. Okay. So this actually then R star will equal sigma n equals 0 infinity a and R minus R a and R minus R I dr, right? You see here, if I equals 0, I have n0 R minus I, so give me log, right? So this actually will give me the following a0 log R minus R I. Plus sigma a equal 1 infinity a and R minus R a. For our Gravitational. So I just consider Gravitational, you can actually usually consider a less than case, R case. So here, this process. Now you can say A0 equal GR, right? The definition, R equal I, G0, because the higher the Y equal 1, this actually R minus R equals 0. So this actually also equal 1 F R. This exactly cover cover A equal cover R. Separate derivative, right? You see now why I introduced separate derivative? So here, the important. I connect this one. Why? Because this is exactly the singularity I have. take this out, right? So then you can say, now, then we have actually R star equal 1/2 kappa I of R minus Ri plus sigma n equal 1 infinity and R minus Ri. Let's call this equation 3. So this actually ER star, what about E2R star? E2R star equal R minus RA 1 over kappa exponent 2 times sigma n equal 1 infinity and R minus Ri, correct? You see now, this is a factor we want to get, right? We want to cancel with the Fi. So now, if we reduce V equal 1 over kappa I E kappa I P plus R star U equal minus 1 kappa I E minus kappa I P minus R star. We have UV equal minus R minus I comma I squares exponent 2 comma I sigma n equal 1 infinity and R minus I. Now you already see the pros why we do this. You see here? This is what we want, right? So if we divide by this one, then after the factor, the exact cancel with it. This singularity disappears. This part is not singular, right? So this actually quite simple. Okay. Now we also want to see what's the D part. P square minus D R star square will equal P minus 2 kappa A R star D dV. Okay? This is exactly equal R minus RA exponent minus 2 kappa see? It's exactly what I want, right? Very simple. So you first need to calculate some of the gravity chi. Then this is always the case. You see here, T plus R star, T minus R star. Okay? This is actually the standard step. ds squared equal f r dt squared minus dr star squared minus r squared. This will be r minus r I g r. Then multiply here r minus r I y x comma. So I have finally together for remember when we write that we were real symbols. So this is not 0, this is not 0. So you can see this acre is perfect okay, right? So we just simply get rid of this. So in this step, like what I said, I just assume this h equal 1 over h. So you can easily generalize this when this is not whole. But all the thing, the singularity here has to be the same. Then there actually allow us to get this concept. The only difference you just define a different GR, then expand. Right? Another trick. So I put F equal R minus R I GR. Why I put it in the denominator? Because I have 1 over F. So I expand this guy to get this one. Right? This actually, this is a mathematical trick. Because this actually, like what I said, is a simple singularity. So this is G R I different from 0. So this actually the same. So if you know this has been done, right? So then you just come back to what we just used, what we are, we, and I, we get the source. I would like to write again. So this is actually our really fundamental relations. You see here T plus R star T minus E2. Why E2? Because we get actually, this guy has a log R minus R star. When we get an E2 exactly, we get a 1 over R minus R stars factor. So here you can see now in this corner, we delta 0, 0, and the U less than 0, you can just simply expand this. Let's forget this expand this V U to the whole plane, then you get extension, right? So this actually, the next service is easier to do the extension. Very simple, right? Very simple, like what I said, it's just like you need to a very simple structure. If it's complicated than what we said, it's not like we cannot do. Not only you cannot do, I cannot do, I do not know anybody can do. Because this is actually complicated. So now we want to say, oh, let's consider Einstein case, right? So let's consider the F equal 1 over 2 mr, right? In this case, you can see F r equal r squared to m, right? So 1 r equal 2 m, this is actually 2m, this 2 m 1. So this is actually surface rotary. So F then kappa equal 1/2 f, let's see, and horizon a, this actually equal 1 over 4 f. This should be 5, right? So you might know that we use this equal to Rg because Rg is defined as Einstein radius 12. This is sometimes use Rg, sometimes use Rs. This is called black radius, right? So R is Rg. And you can also get rid of this cycle, you already know this thing. R plus Rg plus so this actually, I will not repeat it again. This actually E minus Rg over Rg dV. This is exactly the case. Versus in my notes, actually, I just always talk about how to write it down. This actually is one reason, for example, if you want to see, here is a 1, this is 2. You want to see what's the reason, you just follow my notes. I think in last class, I always use P prime and X prime to get the quadrature reason, this one and all the extent. So I will not repeat this again because I want to come to the general case. The general case is difficult. Like what I said, the general case, this is the only one, the only measure we can follow. There is no other actually factor one. So I wanted to spend a little part of time for the general case. Okay? So this actually, you can easily get, once you get this one, the rest of the diagram, then you introduce a Q, PQ, right? You can use actually, I use the V bar, Q bar, you might know that I use PQ. PQ is from minus 2 pi to plus 2 pi, right? So you will do the same thing. So, for example, in the Maxwell case, I have another one. This actually, here written is true. This is actually R plus, this is R minus, this is 0. So you can, we just did it here, you do the same thing here, then glue them together. Okay? So then the whole picture now, once you them together, you need to know how to put them together. So you see, this acre is a charger case, complicated. In this case, you just go to infinity, only infinity. Okay? So I think with this one, you should be able to figure out this, how to do this. Okay? No problem. Once you meet some problem, when you do research, if you have some difficulty, send me email. You have my email, right? So we can discuss together. You will use it again. Any question about this part? Okay? So this is how to, you just make a separate extension, then glue them together. Then in the charger case, you will see the difference is this is like so charger how this charger. This acre, there's an infinite acre. You go to infinite. So what does this mean? No one knows. Even we do not, we are struggling with this one. Here is more common. The cursor also will rotate like this one. Okay. So I will come to the degenerate case. The degenerate case, degenerate case, one example is like what I said, ds squared equal f r d r squared minus d r squared f r minus r squared f r equal 1 minus 2 m r plus e squared r squared. This is actually called child for example. This is a child. So this case, this you can see I have r squared minus 2 mr minus plus e squared. Right? So this acre equals 0. I have r equal, this guy is 1/2 2 m plus minus 4 m squared minus 4e squared. This is exactly equal m plus minus m squared. Okay? So this is called a chart. We have 2 acre solutions. Let's call this plus minus. So r plus m plus. Oh, it's good. Equals 0 case when chart equals 0, then we will reduce the chart solution. This is normal actually problem. This actually becomes singular r 3 times singular. So we are not consider actually, we always consider E different from it. But there's actually H from a case. Which actually m squared equals e squared. Right? If m squared equals e squared, then we have r equal r plus equal r minus equal actually m. Right? So then you see in this case we have actually f equal 1 over r squared r minus m squared. So this is the case of the two rules equal. Then now you can see if I calculate this kappa equal 1/2 f prime, right? 1/2 of prime, you see my f prime equal minus r 2 times r squared r minus m squared plus 2r minus m r squared. So when r equal m equals 0, the separate gravity in this case equals 0, then that's actually standard definition of a U, and we remember we just equal 1 over kappa A E. Let me try. This is going to work, right? You see, here this equal 0 become constant. Also, this is divergent. So there's no way actually to use this solution because this is now we have actually kappa A equals 0. So this actually means in this case kappa A equals 0. So the growth becomes 0. Okay? Then we cannot use this. So that's why, for example, if we have F equal R minus RA, G, R, we have the same problem, right? But if you have something like this, the supergroup will diverge, right? So take the origin, this actually become dominant R equal RA, supergroup will be. So either way, we do not know how to do this. So this actually, the external case actually, what one can do is simply just set P equal tangential P plus R star. Q equals tangential P minus. So you see, when surface growth is different from 0. For the same case, I just do this. For this actual one, you have 0 surface growth, just simply put this. If we do this actually, you can see this actually, the solution will be the following. Will be actually fine. Lessons. using this already, you can prove. This is R star equal to, this guy is exactly, you see here, if I put a square here, I get a square here, right? So I get a square, this is square, this is R squared, you see here? Give me R minus M squared. This is enough to cancel this. So this anchor, you can this is R, you can just work off it. Because this anchor, I can put this guys here, get a square. Then you can tell this will give me R minus M squares, right? The leading. This I can then cancel with this F, our F equal R minus M squares. Okay. So this anchor is an external case. You say now, okay, I have no more singularities. This is called Cartan's extension. So he spent some years to figure out this case. And the very beginning, he was working with Professor Paris in Cambridge. Later he went to France. Actually, this paper he published the result from the America in 1966. The Paris diagram actually in 1964 they did this. Then he actually after 2 years figured out how to do the degenerate case. So this actually the case one can see. Okay, I have also no space time. The space time is also can be extended beyond this double corners. Then after that you will see this actually the extended case. There's actually R equal 0. This actually R equal 0 singular. Okay. So you need to work out the details. I think I'll just put here, give you a reference. If you cannot read my notes clearly, just read the paper. If you have any further questions, let me know. Okay? So this is a case I think we have the degenerate case. This is the only measure we know. Like what I said, we do not know how to deal with, let's say, other cases, but if we have a single actually singular point for f of 0 point, we can do easy. If we have a two root equal, that's fine. If this actually becomes a fraction or whatever, if it's more bigger than 2 or between 2 and 1, we do not know how to do this. So, because this guy is, you can imagine, for example, this is not an analytical function across this part. R equals 0, R equal to n. So the extension will be actually non-analytical. Non-analytical you have your finger with, right? So we do not know how to do it. So any question about this part? So this actually is the Paris extension. Now, any question about this part? Maybe I think I teach, I just pass this part too quickly. I'm sure perhaps you will have questions later whenever you meet the program. Remember me, send me emails. So keep my email someplace in case you need it. Okay? So I would like to discuss this with you. One thing, another particular case I want to see, to actually talk with you. This is case. Now what's happening? They have R equal 1 minus 2n R plus E squares R squares 1 E squares greater than m squared, right? Because here actually we have two is equal m plus minus m squared minus e squared, right? So if this actually the case, this f you will see always positive, right? So f actually, in this case, fr always greater than 0. So this for 1 m squared, that's an e squared. So if it's always no 0, then of course this guy is not singular, right? There's no metric singularity. But the space-time is still singular now, equals 0, right? So what's happening now? In this case, what's the Penrose diagram? So this actually I want to ask. This is a very particular case. What's the Penrose diagram in this case? Huh? We can do the same thing like what we did before. So we have a d s squared equal f r d t squared plus minus d r star squared minus r squared d omega, right? So okay, you can always do this, where r star equal dr fr. So you will get some function. Maybe you cannot sometimes integrate the expression, but no problem, it's the functions, right? So I can do this. So then I can actually I can use this let's see, d, I can use w equal t plus r star v equal t minus r star, right? Then when I do this, I have dx squared equal f r d w d v minus r squared. Right? This guy's not a singular. But I do not have singular, color singularity. Right? So I have actually, you see, g w equal 1/2 f g theta equal minus r squared d phi equal minus r squared. First, g w equal 2 times f g theta minus r squared d phi equal minus r squared. Correct? So since my f are always greater than 0, you see here, there's no singularity unless r equal 0. Correct? R equals 0, this guy is leading, so that's why this f always positive. Right? So now you can say, okay, for finite r, this is okay, this is okay. The only thing is r equals 0 and r equals infinity. R equals infinity, we already know, using my notes, you can use constant coordinates, then you will find no singularity. R equals 0 is a real singularity with no need to care about. So this is actually also finite, often finite, right? So in this case, the problem, how do we do Penrose diagram? This you can see the expansion, right? What's the Penrose diagram? We just want to squeeze them together, right? So this our case, what we want to do actually, we simply let's see, choose V equal alpha tangential V bar dot equal alpha tangential dot bar, well actually V bar dot bar. So the whole plane is mapped into the diamond, right? Then we have actually it's a minus half pi minus half pi. So this anchor is the plane here. This anchor is the 0, 0 point. So use this one. Now remember this anchor, there is a R equals 0 singularity. So I can properly choosing I'm quicker now. Choosing alpha, we can put this angle R equal 0. Sorry. So you can just simply R equals 0 corresponding to this is straight line. So now, this is a point where both of the pi is minus pi. This angle will be this angle pi minus here is the angle minus pi. Okay, so here actually becomes my spin-time singularity. Then I have 1 prime 1. I still have two regions. But this angle, two regions does not connect because I have singularity here. Right? I do this very quickly. I want to later you will see, you will actually, if you want to work out this one. What I want to spend a little bit of time to consider the structure of this one. Later you will find it easy to get it, because this is nature singularity. So the only thing is squeeze them together. So now here it's a nature singularity, it's a singularity, what we call naked. For example, if I'm here, this angle R equal infinity, this is R equal infinity. Then the trajectory will go like this. This is R equal constant, sorry. So you just actually, if the person is moving this is a trajectory R equal constant, then you can see the singularity, if the person here, the singularity, this is actually 45 degrees of mean, right? So this is singularity, I can shine my flash here, then it reaches here, then the person come here, so he can see what's happening here. So suppose an R equals 0, I'm shining fractures, then the light, again, it's 45 degrees, right? The light comes. Then the light that comes in this direction, this person goes this way. When they both meet here, this person sees this single arc, right? In that sense, it's called negative single arc, because I can see, right? So this is actually when, in that case, I have F equal 1 minus 2, and R plus E squares, R squared, A for my E squared, the greater than M squared. This is the Penrose diagonal. So now this part and this part, they are separated by single arc. I cannot pass from here because it's single, right? So the center line, the light still goes to 45 degrees, but it cannot pass from here because single arc. So these are two regions that are separate. But I can, for example, in a vacation, if somebody shine the light, then the light will go to 45 degrees, then this person will see. The physical meaning, he will see what's happening in the naked single arc. This is what's happening in the single arc. That's why we call it naked. There's no horizon curve. Not like celestial solution, the covered by R equal to M, right? Here it's totally naked. Exactly in this sense. This angle R equal constant from like what I said. I'm simply setting the certain distance, let's say, far from black hole. But far from R equals 0, like what we did here, this is R equal 1. So here is 0, this is like single arc. So this actually, this guy is moving along this direction, the large signals will see this exactly this trajectory coming from this point. So see this one, that means this person can see this signal arc. So that's why we call negative. The trajectory, you're going to see this exactly from here to here. Like what I said, I think somebody asked the question, why, remember black hole we have here? This angle R equal constant, right? So here, you see single arc, R equal infinity. So here, symmetry here. We have something point here. I think you asked the question. So this angle R equal constant surface, sit down here. Then anybody, if we give him enough time, he will see the single arc here. So this, in that sense, is naked. But if you want to see here, for example, this is a singularity. Of course, we never see here. This is always in the past. We cannot see. But we can see this. This is called white hole, right? So this guy is showing the signals, remember, 45 degrees? The light goes. So if this guy comes this direction, this direction, we'll meet this signals. So to this person, this singularity is negative. So we call white hole. It's not a negative. In that sense, we have anti-horizons. So this angle, black hole horizon or the white hole horizon, also called anti-horizon. Anti-horizon means just the opposite of the horizon, since the signal comes out. Right? So here, this white hole, anti-horizon, here I do not have horizon. This is negative singularity. White hole singularity can be seen by this over there. Negative singularity can be seen also by this. What's the difference? Is there any difference? Mathematical, now of course they're different, right? Physically, we do not know because we never observe negative singularity. No white hole. Why this is so important? Did you see the YouTube? The interview with Prof. Paris. If you have not seen, go to YouTube. Look for his interview. Do you know what he said? He got a Nobel Prize, right? Because of his singularity theory. This is theoretical. He proposed black hole exists. So we observe two supermassive black holes. When I say observe, actually, Professor Sushant has been working on this for many years. That can be black hole, can be something different. But consistent with the black hole, right? So Paris said, okay, I will change my quotation for Nobel Prize, for my Nobel Prize. Why? Because I used to prove negative singularity cannot exist. Now I think I need to change that quotation. Negative singularity can exist in our universe. And this following natural statement, he got a Nobel Prize a couple of years ago, right? With perfect people. People ask for cosmology, he did this for classical singularity, sure. Then we think he's the father of black holes and lives theoretically. But now he just said, okay, I'm going to change my quotation for my Nobel Prize. Because natural singularity can exist in the universe. I cannot exclude this. Okay. So there are lots of things I want to say. This looks like it's simple, but you see, you guys are in a very good time in the sense of working in this field. I'm glad actually I came finally to India. This is my dream for many years I want to come. In 1997, there was a conference, GR17. I was in Brazil. I tried to get a visa to pass the GR17. But I got a visa after my meeting is over. So I tried coming here many times. This meeting course was originally from 2018. I mean, 2018, but 2019, you know what's happened. 2019 on this point. But I can see you guys are so passionate. We have so many young people want to like to work in the field. So I think that is one of the best time to work in gravity. Very simple argument. We observe black holes, supermassive black holes. We observe gravitational waves. Now we try to test gravitational theory, the strong field regime, right? So before we test the theory, always solar system or others a weak field regime. This is a really strong field regime. Black hole, right? Strong field regime. Gravitational waves, I just tell you, we observe gravitational waves were weak, but they came from the very strong gravitational field sources. The gravitational wave was observed, just the amplitude becomes smaller. But all the information still is strong field. The information was not washed out. Everything there, still here. The only thing is amplitude, small. So we have all the information, right? This is from observational. What about from quantization? We have four forces. We know actually the atmosphere is unified very well by standard model. And the standard model actually, all the particles predicted by standard model was discovered, right? The last one is Higgs boson. I always think it's amazing. If you think in 1958 or 58, 57, people proposed that theory, predict larger particles will appear in our universe. Then, after so many years, we discover one by one, finding all the particles. This is the power of theoretical. Nobody see any particles before, but as the theory predicted, they just find one by one. finally in 2012 we find Higgs. What else are we going to do? We cannot sit down here just drink coffee, right? So recipes, you have to think something to work on. Now it's gravity. Because the quantization of gravity is important. So if I like to give another mini course, local quantum gravity, I have been working on. Father of global quantum gravity is original from here, Professor Aztec, right? You are not. So there's a super string global quantum gravity magnitude. I consider global quantum gravity the best one to work with. Maybe it's not the best itself. The best one to work with is why? Because this actually you can really sit down there to do calculation. For example, global quantum gravity when applied to cosmology, I can really sit down there and write down the Hamiltonians using global quantum gravity ideas to quantize the system step by step. Mathematically, there's no any approximation. Then I can show you exactly Big Bang singularity disappear. Normal singularity, this is what we expect, right? Black hole singularity here, no matter naked or not, physically, this problem, because we do not know what's happening. Fortunately, the black hole, the singularity was covered, so we think, okay, so far has now directly threatened to us, but theoretically it is threatened. It's like the Einstein theory is broken down. Global quantum gravity itself has a lot of problems, but when you apply to cosmology, you can use our basic knowledge, just quantum mechanics. You show people, okay, I quantize this one, I can write a wave function, show you the wave function is now becomes regular and used to be Big Bang. Then you can use some argument. So everything. Okay. This actually the things I think try to open your mind. So we come here this area purely classical point of view, singularity naked or not, but we expect quantum mechanics or quantum gravity will fix them. Why? R equals 0, the curvature goes to infinity. What means curvature? Energy, right? Can we have an infinite energy? Where does the infinite energy come from? Right? We do not expect the infinite energy. So this is the reason why, because we just push the essence until the energy is so high, we still think it's correct. But we have no idea if it's correct. So that's why we believe quantum gravity, once you reach the Planck scales, you need to take a quantum effect into account because the scale becomes so small. Your classical theory, like classical mechanics, will not apply to atoms. We have to use quantum mechanics, right? So the same argument. But after more than 100 years, we're still struggling with the quantization of gravity. This is also good news to you guys. This has been done some years ago. You do not need to think about this. You have to do something else. Okay? So this is a good time. I think Professor Wang used to say, okay, where is the chaos? Where should I go? This is a time, place you can make some discoveries. Right? So this is actually the sense. So I think there was today we just finished the lecture a little bit early. You guys take a rest, then go back to read my notes. If you have any questions, let me know. Okay? So this part is hard, but I think unless you have my contact information and also my notes, go back and read this. If you work on this, I suggest you find some example to work on. Then you will find not so difficult. The only thing you need to face is do step by step, not hard. Okay? Yeah. Okay. So perhaps today we stop earlier, less than 17 minutes. Okay? Yep. Gravitational waves. This is accurate about that.